We are going to pick up where we left yesterday, but I have a few slides of introduction and to connect with yesterday's lecture, and also for those that were not here. Here's the outline of the first part of the first part of today's lecture. We are going to do some review, then we're going to talk about approximation, value space, and neural networks. That's where we left yesterday. Then we're going to discuss model-free dynamic programming, where you can use approximations based on simulation, but without knowing the model of the system, using something called the QFactors. And we explain what that is. Then we are going to talk about rollout and online simulation based cost approximation. So let's do a little bit of review. Remember the exact dynamic programming algorithm. It involves states, controls, disturbances, which are random, a system equation, and a cost per stage. And the objective of the algorithm is to compute for every k and all states xk the optimal cost of the tail problem that starts at xk, which we denote by jk of xk. That's what the dynamic programming algorithm computes, and it does so using these formulas here. We start at the very last stage and go backwards. At the last stage, Jn is just the terminal cost function. It's a function of the terminal state. And then at each time k, state k, we form the sum of the current stage cost and the optimal cost to go at the next state, which is value of that, because wk is random, and this becomes a number that depends on xk and also on the control uk. Minimization over uk gives a number that depends on xk. So we do that for every xk and k going backwards. It's a lot of computation, and this is what motivates approximations. And we talked about one-step look ahead and multi-step look ahead with approximation of the cost function of the tail problem at the end. We replace, in one-step look ahead, we replace jk plus 1 in the dynamic programming algorithm by an approximation j tilde, which we can compute in a number of different ways, presumably easier than finding its exact value. And then once we have j tilde, we can plug it in here in the expression that's minimized in dynamic programming, and we obtain a control that attains the minimum, and this is what we apply at state xk. So the system, once we have j tilde, the system runs, and for every state that we encounter, we do this calculation, and we apply the control that minimized in this expression. Now in L-step look ahead, instead of solving a one-stage problem, a one-stage minimization, we solve an L-step minimization, which involves a shorter L-step dynamic programming problem that starts at xk and uses as terminal cost function some j tilde at the end. And if an optimal policy for this L-step problem starts out with uk bar and also involves some additional control functions, then we just apply the first control. And then we move to the next state. We look at a horizon of L steps again, a rolling horizon. We do another minimization, obtain a control, and so on. And that's the way we go. So that's the basic idea in approximation, what we call approximation in value space, and can be implemented with one-step or multi-step look ahead. And the figure is what you see here. We have, this is the L-step look ahead minimization. It involves the cost look ahead over L steps and a cost approximation of the future. And we discuss primarily parametric approximation. This j tilde here comes from a class of functions that depends on a parameter, and we pick the parameter vector in some kind of optimal way. And this is called the training process. So we have minimization, expected value, and cost approximation. Let's focus on cost approximation with a parametric architecture. And we focused on feature-based architectures, whereby at the given state xk, we extract a vector of characteristics. Let's say a number of characteristics, scalar characteristics that form a vector that we call the feature vector that depends on xk. And then we weigh linearly these characteristics and obtain a linear cost approximation, linear in the parameters. Okay? So that's a linear feature-based architecture. Now, the neural networks that I'm going to discuss are almost linear, but they involve also a nonlinearity, and we'll get to that. Now, once we have the J tildes, we have trained the architecture, we have, the way to train the J tildes is to do this by sequential dynamic programming approximation. We execute the dynamic programming algorithm with approximations, start with J tilde n equal to the terminal cost function, and sequentially train the architecture going backwards until k is equal to 0. So given a cost to go approximation J tilde k plus 1, let's say that we use one-step look ahead to construct a large number of state cost pairs. Now, we sample the state space, okay? We obtain potentially a very large number of sample states. It's xks. S goes from 1 to q. Q can be large, 1,000, 10,000, 100,000. And so we have, and for each one of these sample states, we calculate this expression. Now, we know J tilde k plus 1 from the previous stage, and we plug in xk of S. We know rk plus 1, okay? We have the parameters from the previous stage. So this expression is a random expression with respect to w. Take the expected value, it becomes an expression that involves xks and u. Minimize over u, and that gives us a number. And this is the right-hand side of the training pair. So we select a large number of sample states, we compute the corresponding quantities beta, and then we train an architecture for J tilde k using the sample pairs. So this is our training set, and usually the training is done by some form of regression. We match the approximation architecture to the input-output pairs in a least square sense, okay? So this is an expression that involves q terms. Q can be very large, remember? And for each sample, there is a quadratic term here that depends on rk, and there's also a regularization term at the end, which is, okay, it's customary to perform regression, particularly this field here, by using this regularization term, where r bar is some initial guess, some known quantity, and gamma a positive number, which is a regularization parameter. Sort of keeps the optimum close to this r bar and stabilizes somewhat, tends to stabilize the computation. Okay, start with that at the end, go back one step, calculate the parameter vector Rn minus 1 using this form of regression. Then we go to Rn minus 2, generate a training set, do regression, and go back all the way to k equals 0. And once we're done, we have this sequence of approximate cost functions that we use to generate controls online. Okay, now let's focus on the special case of neural networks. A big issue in this field is how do you choose those features? And you can choose standard features, but neural networks have the advantage that they construct features for us automatically. We can use them in the context of this sequential dynamic approximation scheme that we discussed, train the stage k neural network by using a training set generated with the stage k plus 1 neural network. Okay? And we can view neural networks as nonlinear approximation architectures, but we can view them as linear architectures where the features are automatically constructed in the training process. And they look like this. Let's focus at the typical stage k and drop the index k for convenience, just to simplify the expressions. So this is a neural network at the typical stage, and it has the form, a form which is linear in a set of parameters which we call R, and it involves features, but the features themselves involve a parameter vector V, okay? So there are two parameter vectors here, R, the linear parameters, V, the nonlinear parameters, and they have different roles. The V's define a feature vector, and the R's are the linear weighting parameters that weigh the features. And by training V and R jointly, we obtain automatically generated features. Okay, so how does the architecture look like? How is the training done? What we need is to construct a map that maps states into approximate cost functions. So states come in here, and cost approximations come in here. And what's involved is a sequence of transformations. There's a first preliminary transformation where we take the raw state and we sort of encode it in a way that may be convenient for the computation. I call this state encoding, and it's an optional stage. It may be that this state encoding is just the identity, or it may include some special features of the state, like, for example, 0 or 1 if the state belongs on the right-hand side of the plane or the left-hand side of the plane, things like that. Specialized features that we design ourselves. Okay, so once we have the state encoding, this y sub x, this is linearly transformed in this box here. Now, this is a linear transformation involving a matrix A. Doesn't have to be square. It may have some special structure with some special sparsity pattern, and also a constant vector B. Now, these components of A and B are tunable parameters that the training process will determine. Okay, so now from the linear layer, we have a number of scalar outputs, and these are inputted into a nonlinear layer consisting of one-to-one nonlinearities, scalar nonlinearities that, okay, I denote like this. They don't have to have exactly this form. Each scalar output from the linear unit, from the linear layer, comes in as input in one of these nonlinearities, and out come these features, but they involve these weights of these weights V. They depend on the weights, which are the components of the linear layer. Now, these nonlinear features, I call them features, are weighted with parameters that are the components of this vector R, and out comes the cost approximator. Okay, so the linear layer involves parameters which are the components of the matrix A and the vector B. The nonlinear layer produces M outputs, M inputs here, M outputs here, and they involve this nonlinearity sigma, okay, which weighs the output of the linear layer for each I goes from 1 to M. And sigma is a scalar nonlinear differentiable function, and there have been several types that have been proposed. In the old days, people tend to focus on sigmoidal units. Sigmoidal units are units that are like this, okay? They go flat out on the left, flat out on the right, and they involve some nonlinearity in between. They come under different names and formulas, hyperbolic tangent, logistic function, and so on. Nowadays, people also use an easier, a less complicated form, rectified linear units. A linear unit is the max function, basically, flat and then linear. A rectified linear unit is a version of that where you smooth out the corner so that it becomes differential. And it turns out that, okay, that they have worked quite well in various applications. But there's a large variety of these nonlinearities that one can use. The main thing is that they're differentiable and they have some properties. Okay, now once you have settled in the architecture, that means choosing the dimension of the matrix A, and then choosing the nonlinearity here, then you have a certain training set. Remember, sample states and sample right-hand sides of the dynamic programming algorithm, and we plug them all in to a big regression. Okay, what's involved here? What's in parentheses is a single sample of the training set, XS and beta sub S. It's the output of the nonlinearity, which are the features, and weighted with the parameters R, and we have a quadratic term for every sample of the training set, potentially a very large number, and this optimization is done with respect to A, B, okay, the parameters of the linear unit, and R, the linear parameters at the end. Okay, so this is an optimization. It's very difficult, but people have been able to deal with it using incremental gradient methods. I talked a little bit about incremental gradient methods yesterday. Another name is backpropagation. You can also find the name stochastic gradient descent in the literature, and it involves moving the R, A, and B parameters along sample gradients as opposed to a full gradient of the objective. And this turns out to be much more efficient, and people have achieved success with these problems, and people use these methods quite routinely, in fact. Okay, so that's all I have to say about the training problem. However, how good is this approximation? How potent is this neural network structure? Well, there's an important theorem called the universal approximation theorem that says that if you make the neural network large enough, sufficient number of parameters, sufficient number of nonlinear units, then you can approximate closely arbitrarily complex functions. Now, arbitrarily complex functions means piecewise continuous, for example, are included, but even beyond that. So that's a pretty powerful theorem. And in fact, it persuaded, and in fact, this theorem holds for a single nonlinear layer. And in the old days, when neural networks came into prominence in the late 80s, 90s, people thought that, well, we have this universal approximation theorem. It's sufficient to take one layer, okay? On the other hand, the theorem applied to multiple layers, and I'm going to give a picture for multiple layers later. And in practice, people were using up to 2 layers, very seldom more than 2. On the other hand, more recently, in the last 10 years, let's say, people started using deep neural networks, which involve several layers, in fact, a large number in some cases. And the picture is what you see here. First of all, let me say that there is nothing really deep about deep neural networks. They're just more of the same, just bigger, okay? Just multiple layers. Theoretically, they have the same properties. They just work better for some applications for reasons that we don't fully understand. Perhaps people that have special insights into subproblems have a better understanding, but generally speaking, there's no theory that says a deep neural network is better than a shallow neural network. Just experientially, they work better for some problems. Okay, so we have a concatenation of multiple layers. The output of each nonlinear layer becomes the input of the next linear layer, and that's how it looks. Now, the linear layers may have some special structure, for example, a sparsity pattern. They may be convolutional, they may be enhanced certain operations. And the success of these deep neural networks in specialized contexts like image processing or speech processing, a number of, and also dynamic programming, are not clear, but people speculate that here what we have is not just simple features, but rather a hierarchy of features. Features from one stage drive features on the next stage. So you have a more rich content into these features potentially. And so this can be exploited to specialize the role of some of the layers. And also, as I mentioned, we can use matrices in the linear layers that have a special structure that encodes special linear operations such as convolution and others. The net result is that for many interesting problems, when you use a deep neural network, you can achieve the same level of accuracy, but with fewer total parameters, okay? And the training problem becomes easier, experientially based on studies. Okay, it's an important development, and certainly it's going to be around for a long time. So that's the difference between shallow and deep. Theoretically, they're the same, but in practice, the deep version may work better. Okay, so we have sequential dynamic programming approximation using a parametric architecture, and we go backwards, train a neural network for every stage. And now let's talk about another version of training that does not involve expectations, the calculation of expectations. It's model-free, and it involves these QFactors. Now, what's a QFactor? A QFactor is a function of a state and control pair. So the QFactor QK at state xk and control uk is just the right-hand side expression in the dynamic programming algorithm. It's just the current stage cost plus the optimal cost to go at the next stage and next state. Okay, so you recognize this expression from the dynamic programming algorithm, but the difference is that it's not a function of the state only, it involves state and control. And that's the definition of it, and this is the exact QFactor. Okay, now note that the optimal cost function from the dynamic programming algorithm statement is just the minimum over u of the QFactor, right? The QFactor is this expression that comes in from the dynamic programming algorithm. So from this equation, it just follows immediately that once you have the QFactors, you can recover the optimal cost function through this minimization operation. Moreover, if you look at the dynamic programming algorithm, if you look at this definition, and you note that this jk plus 1 is the minimum of qk plus 1 over u, you can write the dynamic programming algorithm, the exact dynamic programming algorithm, equivalently in terms of QFactors, okay? It's just over a bigger space, over a space of states and controls. It has a bit of a different form because the dynamic programming algorithms minimize an expectation in terms of cost. But in terms of QFactors, it's expected value of minimization. So the roles of expected value and min are interchanged, and mathematically speaking, this has a tremendous difference. Okay. Now, once we have this QFactor DP algorithm, we can approximate it sequentially using an approximation architecture for QFactors. So we introduce here an architecture, a Q tilde that approximates Q that depends on state control and it's parametric. It involves a parameter vector. It could be a neural network architecture. It doesn't have to be. It may be any kind of approximation architecture. And then we can write an approximate form of the dynamic programming algorithm like so, where we replace the Q's with a Q tildes. So this gives rise to a potential of sequential training starting from time n and then going back one step at a time. Train for k plus 1, then train for k, k minus, and so on. Okay, so now let's go into this sequential dynamic programming approximation using QFactor parametric approximations. It has this form. This is the same formula as the one before. And there's a bit of mathematical magic here. The order of expected value and minimization have been reversed. And this has the effect that you can calculate this expected value by sampling, by simulation, with the mean operation being inside, so it's not affected. You can take, you can sample this expression, large numbers, and you will get the expected value. By contrast, if you have min of expected value, you can sample the inside of the expectation and explain and expect to get the same. Big difference here. And what we do is at stage K, we generate a training set involving state control pairs, sample state control pairs, and values beta k, where beta k is not the expected value necessarily, but a sample of this expected value, okay? And we generate this large training set, and then we put them all together into a regression. And there is no need for a model to generate a sample for this. A computer model will be sufficient. To generate a sample of this expectation, all we have to have is a box that for a given state and control generates a random value of the cost and also the corresponding state. So we feed in state control pairs, the computer does sampling and generates cost next state pairs, and that builds up our training set by computing the corresponding value here. So that's how we do the training in a model-free fashion. And there's another major advantage of QFactors. Once we have trained the architecture and we have obtained this Q tilde, we don't have to calculate an expectation and an expectation online. The implementation of the one-step look-ahead control is obtained by this much simpler minimization, which does not involve expected values. Okay. It's a big thing. Very often controls are implemented in this way, even if they are trained in a different way, because of this convenience of not having to compute online expected values. They're implemented in terms of QFactors. So the online calculation of the control is simplified, and that's why you see QFactors and Q-learning so prominent in the literature, as well as a model-free training. Okay, so that's all I have to say about Q model-free approximate dynamic programming. And now let's go into another method for cost approximation, which is rollout. Rollout is a simulation-based approximation in value space. So again, we have the same approximation in value space diagram. We have a look-ahead minimization that involves a number of steps, one or more, and we have a cost approximation at the end, which summarizes the future. It's an approximation of the tail problem that starts at this state. And simulation comes in here through this rollout. And what we do in rollout is we calculate this as by simulation using a fixed policy. So we have some policy that may be good or not so good, and we run it forward. We do simulation from every state of interest. We obtain this number. We'll look ahead minimization, and perhaps we may cut some additional coordinates here, but let's not go into that. So no parameters here, okay? No parametric approximations, no neural networks, none of this stuff. It's just simulation with some reasonably good policy. Okay, so formally, rollout computes the look-ahead functions that are needed in single or multi-stage look-ahead as the cost-to-go functions of some suboptimal policy, which we refer as the base heuristic or the base policy. So you have a heuristic and you use it to roll out to get these cost-to-go approximations, and that's the idea. We may use it in one-step and multi-step look-ahead. And If you have a policy that you can calculate its cost function analytically, that's great. Otherwise, you can use simulation. And then you can plug them into this one-step look-ahead minimization to calculate the control, the rollout control. So we have the base policy and the rollout policy using the base policy. And what we're going to show you a little later is that the rollout policy is always better than the policy. So you can always improve this policy that you have through rollout. Let me mention a variation of rollout. Rollout involves simulation from a given stage to the end. If the horizon is very long, then you might want to do simulation over a limited number of steps to save on computation and replace the remainder with some approximation. So that's what I have here. The base policy cost may be approximated over a limited rolling horizon with a terminal cost approximation added at the end. Simulation is used very often for the needed values of J tilde. And as you can tell from what I discussed, the amount of simulation may be very, very large, may be overwhelming. However, parallel computation helps because all the simulation can be done in parallel. And there is a special case where the simulation cost is not as large, which is the case of a deterministic problem. If you have a deterministic problem, there's only one trajectory to simulate forward. So that simplifies the calculations a lot. And rollout has proved to be very useful in deterministic problems of a combinatorial character. It has been used for combinatorial problems as a legitimate suboptimal control method. Now, the major fact about rollout is that the rollout policy performs at least as well as the base policy. So if you have a good base policy, you're going to do even better with rollout. It is often dramatic, and it's also consistent. Out of all the methods that I'm going to discuss in these lectures, rollout is the most reliable. You can count on it to do well. It doesn't, it's not going to, it's not going to crap out on you like some of these other methods. You may not, it always works. And it may not work as well as some of the other methods, but it's more reliable. And the reason why this property holds is that rollout relates to the method of policy iteration from infinite horizon dynamic programming. Basically, rollout is one step of policy iteration. And I'm not going to go into policy iteration, but what I want to impress on you is that there's a theoretical reason why rollout performs consistently well and often well. Okay, so now let me give an example of rollout. Where did the name rollout come from? Well, it came from the game of backgammon that I know many of you are familiar in Greece and in Cyprus. There's a fellow called Tesoro who spent a lot of time in the 90s building backgammon computer programs. Tesoro is a major figure in artificial intelligence. His name has been associated with quite a few successes, including recently for the game of Jeopardy that you may have heard of. A game. He was one of the architects of that program. And in 1991, Tesoro designed a backgammon program that used a method called TD lambda. One of the most prominent methods of reinforcement learning is called TD lambda. And this is what put TD lambda on the map, because at that time, this accomplishment was so impressive that not only he built this backgammon program that could play the game, but also that learned on its own to play the game using self-generated data, but also that program could play almost as well as the best human backgammon players. It almost beat the world champion. Now, in 1996, TD lambda was based on neural networks and parametric approximation. In 1996, it came out with a different concept, which was the rollout. And the way works in Tesoro's programs as follows. You have a certain backgammon position, and you have a certain role, like 6 and 4. And there are several different ways that you can play this role, and it gives rise to a number of different positions from the starting position. And now, in Tesoro's program, from each one of those positions, it rolled out many games, okay, using some backgammon player that a relatively crude, in fact, backgammon player, which was developed with other methods. It was sort of a derivative of the earlier backgammon program that he had. We are at a given position. We roll the dice, and there are several different ways to play. And for each different play, we roll out games to the end, 1,000 games, let's say, using some kind of a player, and then we average the results, and from whatever position we get the best result, that's the position that we go to. That's the way we play the role. Okay. It's involved quite a bit of computation, and that's okay. First of all, the name rollout comes from there. You roll out games, and it's stuck as a more general name for simulation. The other thing is that you had to roll out many games to the very end of the game in order to obtain the score and to average them. So we're talking about a lot of computation here. However, it played slow because all of this computation is online. However, it played well and competitively against the best humans. And that's how the program basically worked. It involved this base backgammon player. It involved also some handcrafted features that guided the simulation. And it was a great success at that time.
You roll out until the end, or for a certain number of moves?
I think you roll out until the end. But I think subsequent versions of the program use what's called adaptive simulation, which is the next slide. And incidentally, you can play with backgammon program. The success was replicated by other researchers. If you go on the internet and you say roll out backgammon, it will give you a very strong game. Okay, be prepared to lose. Okay, so now here's a variant of rollout. In rollout, we are at the current state. We look at all the possible controls, and then we run a simulation from there. Basically, we calculate by simulation the Q factor associated with this state and this control. So we calculate by simulation from here on, and then from here, and then from here. Now, during the simulation, it may become apparent that some controls are not good because you get scores that are inferior. You get large Q factors. You want to find the control that has the minimum Q factor to select, but then suppose that you sample them in turn, and as you do this sampling, the running score of some of the controls is way too high. Then, using some statistical criteria, you can just discard that control. And then first you discard one, then you discard another, and in the end you're going to be left with fewer controls after doing much less simulation. This is called adaptive simulation. Adaptive in the sense that, the amount of simulation you do depends on the results. There is a theory around this technique, and using various forms of confidence intervals, you can decide when to discard some of the controls. There are also versions of this that extend that for multi-step look ahead. And here's another variant of rollout. Here, in the original form of the method, you roll out all the way to the end of the horizon. On the other hand, it is possible to roll out only for a fixed number of steps, and then use a cost function approximation for the remainder. So if you have some cost function already trained, you can use it in conjunction with rollout in order to speed up this calculation. Okay, now here's further enhancement of this idea of rollout, which is called Monte Carlo tree search. It's receiving a lot of publicity these days. Again, we have to compute a control at the current state, and we do this by minimization, and by minimization over a horizon, and then by rollout to approximate the terminal cost. However, in addition to doing adaptive simulation based on the results of the calculation, you maybe want to explore further the potential of some of the controls that appear to be promising through multi-step look-ahead. You may have several candidates, we're not quite sure which one to choose, and then you may want to push them forward in a multi-step look-ahead to make a better decision. So that's what it involves, rollout of various types with various approximations, and also selective depth look-ahead. And there are many different ways you can do that. There's some theory about that. There are some algorithms that have been used in practice that have achieved a fair amount of prominence. And it's also used in the AlphaGo program. This type of method is used in the Go program that created a big impression about a year ago. So let's go into that. This Go program played with one of the best players in the world and defeated him decisively. And what was impressive about that is that experts thought that a human-level Go program was 20 years away, because Go was considered a much more difficult game than chess or backgammon or any of the other games that people have tried. Because Go is very subtle and it's very difficult to figure exactly how to calculate a cost function. So the way these people at DeepMind managed to build this program involves several ideas that we have discussed here. Rollout, cost function approximation, heuristics, and more than anything else, awesome computing power. Okay? So what does it involve? It involves multi-step look-ahead, selective depth look-ahead with Monte Carlo tree search. Now, and also rollout with a rolling horizon which is adaptive and uses a cost function approximation and also some base heuristic. Now, the cost function approximation is computed offline with a deep neural network. So there's offline computation to compute some cost to go approximation, and then it's tucked onto a rollout with some heuristic player to obtain the best move at each position. Now, the base policy of the rollout is also computed offline. The QFactors of that policy are obtained, and then it's and again there's a reinforcement learning type of computation to obtain this base policy. It's very sophisticated. None of the techniques is new, but it was the right mix of the techniques that worked on this problem, and something else. There was massive online computation. The figures that I've read is that during this match with this player, the computational setup involved 1,920 CPUs and 280 GPUs, all working in parallel. And the bill, just the electric bill for a single game, was $3,000. So we're talking about massive computation, but nowadays we can do that. A lot of it, of course, here was done in parallel. Is done in parallel because all this rollout is parallelized. And the offline compute, this is just the online bill, electric bill. For computation offline, of course, that took months of effort to develop base policy and to develop the cost to go approximation.
I ask a question. Is there a measure of the equivalent amount of power that the player used? They play the game?
Brain power.
Yeah, we have a measure because it depends how many watts each one used, right? The power is very important. You know, how well we do, right? It depends on how much consumption cost we allocate when we play.
I'm not sure I answer the question.
Okay, my point is this. Okay, for the online computation, it costs $3,000. So that corresponds to a certain amount of power used. The human who played, how much power did he use? Then I can compare. That's my point, because power is a big issue. It is a fundamental limitation of how well we do, as far as I understand.
I'm sure this figure of 3,000 is going to be improved in the future. So it may cost $3 rather than $3,000. I don't know, I can't answer this question. Certainly there was no problem, there's no issue with cost because this was funded by Google. So they had deep pockets. They had $3,000.
It's not a matter of money, it's a matter of how much watts were consumed when the online computation was executed.
I don't know how it translates to watts.
Yeah, that's right.
Yeah, okay.
Okay, let's take a break here and we go into approximation in policy space when we come back, 5-10 minutes.
5 minutes, yeah.
There's a question here, just one moment please.
We said that we start from a base policy and do the rollout simulation, we end up with a better policy. Oh, sorry.
Yes, better. So we say that if we start from a base policy and do the rollout simulation, we end up with a better policy. Are we doing the best we can do the first time, or we can do an iteration and give the new policy at the start and always do better? Does it make sense?
Well, the rollout policy is counted from time 0 to the end of the game. And in theory, it will do better. Now, the way it was implemented, who knows if the theory applies. But definitely, the rollout player, in the case of this program, worked much, much better than the base policy.
We take the rollout policy, so the better one, and give it back to another rollout simulation, will always do better, and up to some extent.
Yeah, this is a possibility, but the computational cost increases exponentially. With each level of rollout, you can do rollout as many times as you want, but with each level, you have an exponential increase of the amount of computation. So in simple cases, in deterministic problems, people have tried several levels of rollout, but not with stochastic problems. It's extremely difficult, extremely time-consuming. Yes?
I have a question from this neural network that why do we need this nonlinear layer, and how can we include this sigma in tuning process then?
Why do we include a nonlinear layer? If we don't know features that sort of encode the nonlinearities that are important in our context, then it's nice to have a nonlinear architecture because it offers the potential of a richer set of possibilities. And what was the other part of the question?
Like for linear part, the tuning parameter we can calculate using least square or recursive least square. So how can we include this nonlinear in tuning? How we will decide what nonlinear function do we need in this layer? Like for other we decide weights. So for nonlinear layer, how we will decide the tuning?
You mean what kind of nonlinearity would we use?
Yes.
Well, there's no theory for that, really. And it's all problem dependent and a matter of experimentation. It's a combination of performance and convenience and so on. So the sigmoidal units are richer than the linear rectifiers, but the rectifiers are simpler and they simplify the computation. I really don't know how to, I really don't know of any criteria to prefer one nonlinear architecture over another.
Okay, thank you.
Sure. Yes?
The QFactor that you mentioned is similar to the Q-learning.
Yeah. Q-learning trains QFactors.
Right, so in your questions, I didn't see the discount factor.
Okay.
Which is normally in Q-learning and reinforcement learning theory.
Okay, I'm using the term Q-learning in a more general, with more general meaning. Anything that trains Q-factors, I would call Q-learning, but Q-learning is usually presented for infinite horizon problems and primarily for discounted problems, and I think that's what you refer to. Then the Q-learning algorithm is a little different than here. It's not sequential, but rather it involves sampling as we go.
When you look in the future, when you have a look ahead sort of algorithm, you have to look at discounted sort of states of the future.
Okay, so this is the Q-learning algorithm with approximation, and it would involve a discount factor over here. Okay, and this expected value is usually given in the literature in terms of sampling. You generate samples of state controls pairs, and then you generate samples of this expression, you discount them, and then you move the parameters. It's an iterative algorithm for the RK parameters. This is a little different kind of Q-learning because this is a finite horizon problem. It's not an infinite horizon problem.
And just one more thing, I'm not that familiar with the rollout, but isn't it similar to the temporal difference type of learning in a way, which again you look ahead and you're kind of trying to minimize the error, or the future error in a way.
Rollout is much more time consuming. There are different things. Temporal difference cannot be applied online very easily. Rollout is very well suited for online calculations, but also a lot of computation, a lot of simulations. The computations of temporal differences is also very significant, but it's done offline. Rollout is also more reliable. Temporal differences, like I said, it always works, provided you have the computational resources to implement it. But temporal differences, well, if you look at the literature, you'll get a more favorable picture than what you get in practice. And there are also several different types of temporal difference methods, some of which are better and more reliable than others. But we're not going to talk, unfortunately, we just don't have time to go into infinite horizon problems and temporal difference. It's a fascinating theory with very rich methodology and has been applied very widely. Some of the temporal differences have been used, in fact, in the AlphaGo program in one of the offline calculations. So there's so many ideas involved in that program.